What if, tonight, without any warning, the universe stopped expanding? The concept is both fascinating and terrifying. Imagine the cosmos enveloped in silence, devoid of any cataclysmic events such as explosions or alarms. It would be just another night, yet the implications of such a scenario are vast and complex. Currently, the universe is in a state of continuous expansion. This expansion is not merely the movement of galaxies drifting away from one another, it is the very fabric of space itself stretching outwards. Every passing second sees the universe's boundaries extend farther, and the void between galaxies swell. But what if this expansion came to an abrupt halt? Not a slowdown, not a gradual weakening, a complete cessation of movement. We might wonder if we would notice this change immediately. Would our day-to-day lives on Earth alter drastically? Or would this unprecedented cessation of universal expansion lead to a quiet, almost imperceptible transition into a new cosmic reality? To comprehend the consequences of such a halt, we must first delve into the fundamental forces that sustain our universe. Following the Big Bang, the initial explosion propelled everything outward, fabricating space itself. For billions of years, gravity served as a counterforce, relentlessly pulling matter back together. In the early universe, gravity appeared to be the dominant force, exhibiting its powerful grasp over cosmic materials. However, about 5 billion years ago, a curious phenomenon emerged: the acceleration of the universe's expansion. This was not a deceleration, but rather an increase in speed, an unexpected twist in the narrative of cosmic evolution. Scientists designate this elusive force dark energy. The term dark does not imply malevolence, but rather a profound lack of understanding about its true nature and origin. Dark energy constitutes a significant portion of the universe, while dark matter also plays a crucial role in the cosmic ballet. In contrast, the observable universe, comprised of stars, planets, galaxies, and life as we know it, makes up only a minuscule fraction of all existing matter and energy. Essentially, dark energy fuels the ongoing expansion that keeps galaxies moving away from each other, preventing the universe from collapsing inward. Now, let us entertain the notion that dark energy, the very force that propels universal expansion, suddenly vanishes. Or imagine it becoming weakened or even reversing. Initially, life on Earth would seem unaffected. The Earth would continue its rotation, our Sun would shine just as brilliantly, and the Milky Way would maintain its familiar appearance. No immediate tremors or cosmic disturbances would signal a shift in the fundamental nature of the universe, and therein lies the true terror of this scenario. The most hazardous changes in the universe often unfold with a slow, creeping inevitability. Over billions of light years, galaxies would gradually cease their outward drift. Their velocities would slow down, transition to a halt, and for the first time since the birth of the cosmos, the universe would hold its breath, frozen in a moment of stillness. However, gravity, ever the relentless force, never ceases its pulling. Although it may have appeared to play a losing game, the instant that expansion stops, gravity would regain its hold on the universe. Galaxies that once raced away from one another would begin to drift inward, creating a scenario where clusters of galaxies experience catastrophic collapses. Imagine the scale of cosmic collisions beyond human comprehension. Stars would be ripped from their orbits, and solar systems would unravel under newfound instability. Entire galaxies would collide with one another, resulting in massive bursts of light and energy, seemingly at odds with the tranquil sky we observe today. As black holes merge, they send shockwaves through the fabric of space itself, producing ripples of energy that propagate throughout the cosmos.
As these gravitational shockwaves propagate through the cosmos, the universe would transition into a new phase characterized not by expansion, but by a gradual collapse. This theoretical scenario, often referred to as the Big Crunch, reflects a reversal of the Big Bang, where the universe, which previously expanded from a singularly dense point, would embark on a slow journey inward. Initially, this shift would be nearly imperceptible. Despite galaxies starting to drift toward one another, the immense distances involved would mean that billions of years would pass before any noticeable effects emerged in local regions. Civilizations on Earth could rise and fall, blissfully unaware that the universe was, in essence, changing course. The night sky would remain familiar, stars would continue to shine, and life would persist for a time. However, on a cosmic scale, significant changes would be occurring. Galaxy clusters would become denser as the force of gravity intensified. Intergalactic spaces would diminish. The frequency of galaxy collisions would increase, resulting not in catastrophic crashes, but rather in slow, spectral mergers that introduce disorder within star systems. Orbits would become unstable, leading to the birth of new stars while others would be scattered into the void. As the universe's contraction progressed, the background radiation, the lingering echo of the Big Bang, would grow more pronounced, leading to a gradual heating of space. After billions of years of cooling, the cosmos would ultimately reverse its course. Eventually, the night sky would transform. Distant galaxies would shine with greater brightness, not due to increased light output, but because their proximity to us would increase. The observable universe would reconfigure itself, with objects that were once lost beyond the cosmic horizon re-emerging as space folded back upon itself. Astronomers would observe extreme distortions of space-time, as vast regions of the sky became stretched and warped by gravity. At some point, conditions would become inhospitable to life. Stars would deplete their fuel at an accelerated rate, radiation levels would rise, and planetary systems would grow unstable. Even if Earth managed to withstand these transformations, the essential conditions for sustaining life would deteriorate. The universe would become increasingly unwelcoming to complexity. As galaxies merged, their central black holes would amalgamate into massive entities, disseminating tremendous gravitational waves throughout space. Over time, matter would coalesce to such a degree that the distinctions between stars, planets, and galaxies would blur, melding into a compact and heated cosmic state. In this environment, atoms may cease to exist, leading to relentless collisions among fundamental particles. Both space and time would start to lose their conventional meanings. The universe would begin to evoke its own inception. What lies beyond this point remains uncertain. The collapse may culminate in a final singularity, an absolute conclusion, or, as some hypotheses propose, this compression could spark a rebound, triggering a new expansion and giving rise to another Big Bang. This new universe would emerge from the remnants of the last, devoid of any memories of its predecessor. If this scenario holds true, then it follows that endings could merely be transitions. If the universe were to halt its expansion tonight, the end would not arrive in a dramatic explosion or with any forewarning. Instead, it would unfold quietly over unimaginable epochs, beneath a seemingly unchanged sky. The most disconcerting conclusions are not those that arrive suddenly but those that begin softly, long before anyone notices their onset.